Hi guys, my name is Tensor. Welcome back to the Rust Snake Game WebAssembly project. This is part 2 and we will be finishing the project in this part. Before we get started building any of the code, let's just clean up some of the stuff that we built yesterday just to test out the canvas renderer. I'm just going to take all of this stuff inside of the main function and just remove it completely. Let's now create the snake submodule for this application, and this is the module that will hold most of the game logic as well as the snake logic for the application. The submodule will be called snake, and naturally the actual file will also be called snake.rs. For this submodule, we want to make an import for our canvas structure. We also need our direction structure, and we're also going to need the Stdweb unstable try into type and trait. First, we want to define a struct called block, and this will just be a named tuple of U32s. Now, basically, the block will represent a position inside of our canvas. So each block will be a piece of the snake or the apple. Each of the numbers inside of the block will represent the x and then the y coordinates of where the block will sit inside of our scaled coordinate plane. For this block structure, we need to derive the debug, copy, clone, equality, and partial equality traits. Now let's create the struct for the snake itself. We'll make this public, and we'll just derive debug just in case we want to debug the actual snake itself. Inside of this snake struct, we'll have the head, which will be a block, which means that it has two positional numbers. Then we'll have the tail, which will be a vector of blocks. And then we'll also have the food, which will also be a block. We also want to enter in the height and the width. Now this is the height and the width that we're going to use to scale our canvas, and we want to attach it to this structure as well. And finally, we want to add 3 different direction fields to this snake game. Each of them will have a particular use case. So first we have direction, which is an option of direction type. This means that it can be either none or some with a direction inside of it. Then we have next direction. We'll use this to hold another option of direction type, and we'll use this in very specific cases to allow us to replace specific directions that the user is entering in. And then finally, we'll have our last direction, which will simply just be a direction type rather than an option of direction type. Now our last direction will always have a direction inside of it, and we'll use this to determine where the snake is moving. When our snake is moving around the board, it initially starts with a direction. Let's just say it's moving to the right. In a frame, when the user hits up button, it will then change its direction to up for that frame, and then that direction will be passed into the last directional field. If the user then tries to push down, that direction will go into the direction field, and then it will be placed into the next direction field because it is opposite of where the actual snake is headed. Now let's build our implementation block for this snake structure. Let's start by defining a new method, and we'll have this be public. It will take in a width and a height, and then it will output our snake. As mentioned before, the width and the height are what we're using to scale our coordinates and make it so that the blocks of the snake and the apple are all consistent so that our snake will be able to actually eat the apple. When creating our new snake, we want to generate the snake head positions based on a random number generator, and we can make use of the JS macro to do so. We're using the JS macro to access the math library inside of the core of JavaScript. So we're using the math floor function, and we're using the math random function to generate a number which we multiply by the width that we're passing into this function. Then we want to use try into to cast that number into U32, and then of course we want to unwrap that number from the result of trying to cast it into the U32 type. We'll do the same thing for head y, except this time, rather than multiplying the random number by width, we're going to multiply it by height. Now let's actually get both head X and head Y and then create a new block tuple and then call it the head for the snake. Just like with the head of our snake, we want to define where the initial food position is based on a set of random numbers. For food X, again, we're going to use the math.floor and math.random functions from JavaScript, and we're going to multiply it by width. And then for food Y, we're going to do the same except with height again. And of course, we still need to call the try_into function and unwrap the result. Again, we can take the food X and food Y and couple them together inside of a named block tuple. Afterwards, we can create the tail by defining a new empty vector. And if you want to, of course, you can make it so that the snake has a tail by default when you create it. But in this case, we're just going to have our snake just have a head when we initially create it. Finally, at the end of this method, we're going to create our new snake struct, pass in the head for the head, the tail for the tail, the food for the food, the height and the width for height and width. And then for direction, we're going to set it to none by default. We're going to set next direction to none as well by default. And because we want our snake to just be moving in a right direction as it starts, we're going to set the last direction as direction right. Now we need to create a method which will allow us to change the direction of the snake when we get a new direction. This method, of course, will be public, and we'll just call it change direction. It will take in a mutable reference to self, which is our snake structure, and then it will also take in the direction that we want to apply to our snake structure. First, we're going to apply some Boolean logic to our snake. So we want to see if the negation of the last direction of our current structure or our current snake is opposite to the direction that's being passed into this method. Now remember that the opposite method that we created produces true when a direction is opposite from another direction and false when it is not. We also want to check to see whether or not direction itself is just none. In other words, it just has none inside of it. We're going to take the direction that's being passed into this method, wrap it inside of a sum type, and then pass it into our self.direction field. We want to take the current direction inside of our structure, iterate over it, and then pass it into a closure where we're checking to see whether or not it is opposite of the direction that's being passed into this method. So down here we're checking to see if the direction field itself is opposite from the direction that's being passed in here. Then we take the direction that we're passing in here and we put it into our next direction field and wrap it in a sum. So in other words, if our direction inside of our structure is not opposite to the direction that we're passing into this change direction method, then we're putting that direction into the next direction field of our structure. Now that we have the change direction method defined, let's create an update method, and we'll use this as sort of a small little update loop for our snake. This is just a public method that takes in a mutable reference to our snake, and we'll use it to update the various properties of our snake based on the various conditions of what happens to the snake. We want to check to see if the direction part of our structure has a option inside of it, meaning it has some direction inside of it. And if it doesn't have a direction inside of it, then we'll just grab that direction from our last direction field in our structure. We then want to make sure everything is consistent, so we'll take and we'll set our last direction equal to the direction that we just defined here. After having done that, we can now match on this direction and create a new snake head using this pattern match. The direction for where the snake is headed can be one of 4 different types. We can have direction up, direction down, direction right, and direction left. And for each of these cases, we want to change how our actual snake head is moving with respect to that direction. So for direction up, we're defining a new block where we're taking the current snake head's first value and then taking the modulus of that by our width. So this is just rescaling our head based on the width and the height that's attached to the struct. Then for the y-coordinate of our block as it's going up, we subtract 1, and then we want to rescale it so that it is scaled with relation to the height by using the modulus function. Our snake head is just moving upwards in the y direction. For direction down, we do the same thing, except this time we're going to add 1 to the y coordinate. So say our self.height is 20 pixels, then we're just adding 20 pixels to the self.head y coordinate of our snake head, so that it moves in increments of 20 pixels. For direction right, we're doing the same thing that we did for direction down, except we're doing it to the y-coordinate, and then we do the inverse for direction left, where we have self.head.0 subtracted by 1, and then modulus of self.width. So we're quite literally creating a new head every single time our snake moves in a direction. Once we have our new head, to actually simulate the movement of the snake, we're going to pass our old head into the tail, and then we're going to pop the end of the tail out of our tail. So if our head is the only thing we have and we have an empty tail, as the head, say, moves upwards, it will then move upwards, create a new head. The old head will go into the tail for a split millisecond, and then immediately be removed. When we eat an apple, we can stop this tail.pop feature so that we actually extend the size of the snake. Now we want to check to see if our self.tail contains a reference to the new head that we created up here. If it does, then we want to take our self and set it equal to a call to snake new with our self.width and self.height inside of it. This means that we've run our snake into the tail and we want to restart the game. After we make this check, we can then officially take the new head and replace the old head with it. So we just say self.head equals new head. And then we can create the logic for whether or not the snake has eaten any food. So we want to see if the self.head is equal to self.food, and if it is, then we want to set a variable which is mutable food equal to self.food, and then we want to run a while loop that checks if food equals self.head or self.tail contains a reference to our food. So if the food is inside of the tail, that means that the snake has run over the food. If we do eat the food, then we'll generate a new piece of food like we did inside of the snake new function, where we create the x and y coordinates by calling math.floor with math.random inside of it, and then just multiplying them by width and height. And we, of course, want to then bind both of these into a new block. Outside of the while loop, we'll take this new food and we'll put it into the structures food field, so self.food equals food, and then we'll take the last end, which we created up here, which is the end of our tail, and we're going to map over it and then just push it back into the tail of our snake. So if we eat the food, we generate a new piece of food, and then we add a segment to the tail. Finally, we want to take our self.direction and set it equal to self.next direction. So this will then convert our next direction into a none value, and then take the direction and put it into self.direction. And that's all we want to do for our update method. So now finally, let's create our draw method. So thus far, we've created all of the functionality that we need to make our game work properly, but we haven't made it so that we actually render the snake yet. Our draw method will be public, of course, and it will take in a reference to our snake structure and then our canvas element. And first we want to just wipe our entire board. So every single time a frame moves forward, we wipe the entire board to white, and then we redraw everything on the frame. After clearing the board, we want to draw the actual snake head. So we'll call canvas.draw and we'll pass in self.head.0 and self.head.1 and then the color of the snake, which we'll have be green. Afterwards, we want to destruct the self.tail block tuple. So we use a for-in expression. This basically just says if there's a block with an x and a y inside of our self.tail vector, then we can destruct that block into an x and a y coordinate, and we can just pass them into our canvas.draw function here, which will then draw each of the blocks inside of our tail. Finally, after drawing the head and the tail, we want to draw the food, and this time we'll just call canvas.draw with self.food0 and self.food1, and then we'll pass in red to make the color of the food red. And that's it for our snake module. So now let's go into our main.rs file and tie everything together to make our game work properly. Inside of our main.rs file, we want to import from canvas the canvas type, from direction the direction struct, and from snake the snake struct. We also want to make a few imports from Stdweb. We need to bring in a glob import of the traits from Stdweb, and we also want to bring in the event keyDown event, which will allow us to interface with the keyboard, and then the iEvent target. The iEvent target is an interface that allows us to add event listeners to various different elements that can have them. There are two more imports that we want to make, but this time they're from the standard library of Rust. We want to import standard cell ref cell. We're going to use this ref cell to allow us to create a reference that adheres to a dynamic set of ownership rules. So this will make it fairly easy for us to apply the ownership rules to our snake. We also need to import standard RC. RC stands for reference counted pointer, and this is again also going to allow us to properly share the information inside of our various structs with one another without having to worry about all the different ownership rules. Now that we have all of these imports, let's start building our main function. We can create our canvas element by calling canvas new and passing in the ID for our canvas, as well as the scaling that we want. And I want every block inside of our canvas to be 20 by 20. Now we can create the new snake, and we can do this by wrapping it inside of an RC and then a ref cell, and then calling snake new and passing in 20 and 20 for the width and the height. I did make one minor mistake with our draw method inside of our snake module, and that was to make the canvas that we're passing in here not a reference. So now inside of the main function, we can call snake.borrow, which borrows the snake from the RC and ref cell, and then we can call the draw function and pass in the reference to the canvas that we defined up here. Now let's create the event listener that we want to attach to the document, and we can just call Stdweb document.addEventListener. Inside of this event listener, we want to clone our snake struct, and this is why we derived the clone and copy traits from our snake. Now we can create a move closure, which takes in the event from the keyboard, which is a keyDown event, and this will then allow us to assign the direction based on the key that the user has pushed on their keyboard. So we want to match on event.key, and we want this to be a reference, so we pass in the asRef method. And for this, we're going to match on various different strings. So we have arrow left, arrow right, arrow down, and arrow up. When we get arrow left, we call our snake. We're going to borrow it as a mutable reference. And then we're going to call the change direction method on it, and then pass in direction left. Then for arrow right, we're going to do the same thing except for direction right. Arrow down, same thing for direction down. And then arrow up is the same thing for direction up. And then finally, for all other cases, we just need to create an anonymous case, and that's what we've made right here. So this little listener listens on the keyboard and then allows us to control the snake. Now we want to create a small little inline function which will act as our game loop. Our game loop function is inline here, and it takes in the snake, which is inside of an RC and a ref cell. Then it takes in the canvas, which again is inside of an RC. And then finally, it has a variable which is the time, which will pass in as a U32. Now the time will just be the amount of time between each of our frames and each of the times that we render a new snake. So if we want to speed up the movement of the snake, then we just have a smaller period of time between when we wipe the board and when we create our next snake. And we can create this timeout by just calling Stdweb web set timeout, passing in a callback, and then passing in the actual time that we want to use to time out our snake for. So inside of this set time callback, we'll create a move closure, which takes in nothing. And then we can recursively call our game loop, passing in a clone of our snake and a clone of our canvas, as well as the time. Afterwards, we can then take our snake and borrow it as a mutable structure, and then call our update function. And then we can take our snake again, borrow it as a normal reference, and then call the draw function and pass in a reference to the canvas. We can pass time into our set timeout function here as the second parameter. Down below where we define the game loop, we can call the game loop, pass in our snake variable and our canvas variable wrapped inside of a RC, and then pass in the time that we want to use. In this case, it's 100 milliseconds. And that's all we want to do for our application. So now we can jump into our terminal and run the application using Cargo Web. So here we can just type in cargo web start -- target equals wasm32 unknown, and this will create our server on localhost 8000, which will then serve the item inside of our static file as well as our generated JavaScript and WebAssembly. And here you can see our application. So here we have the snake, and we can eat the red apples, and if we cross the apple, it then adds to the snake's tail, which is a light green. And if we cross through the canvas, it will then produce our snake on the other side of the canvas. So rather than having a collision check to see if the snake hits the wall of the canvas, we're just making it so that the fail state for this particular snake only happens if we run the snake into itself, like this. So you can see after the fail state happens, the snake then automatically respawns as a simple head, which we can then control to grab a new apple. And actually, I want to do one more thing before we finish this project, and that is add a border to our canvas. We can add a style block in the head of our index.html file, and then we can grab the ID of the canvas and add an outline property where we put in a black outline that is 3 pixels in width and has a solid line that represents it. So now when we reload our application, you can see here, we can see the actual edges of our canvas, and now we know where the snake will then wrap around the screen. Alright guys, well I hope you enjoyed this tutorial project. If you did, feel free to like and subscribe. If you have any questions or comments, feel free to leave them in the box below. And if you disliked this video, then by all means, downvote it as much as you like. Have a good day.